2011, he was elected a Fellow of SIAM for his contributions in bringing together mathematics and industry in the areas of numerical linear algebra, random matrix theory, and parallel computing. And then in 2018, he was elected a Fellow of the IEEE for contributions to the development of technical computing languages such as Julia, which he is going to talk about today.
Thank you, Ann. So it's a great pleasure to be here. I wasn't quite sure whether I should kind of give a math talk or a computing talk, but somehow it's going to be a computing talk. In fact, what I'm going to do is give a repeat of the prize lecture that I gave yesterday in Denver. So this is actually the prize that I'm most excited about in a way, because this is what I'll tell you a little bit more in a moment, but Julia was really created for the purpose of parallel computing, for HPC. And in a way, it's been a little bit tricky and difficult to sort of promote Julia in that area until yesterday when I won the Fernbach Award and gave this lecture at the Supercomputing conference. So what I'm giving is a kind of encore performance for you to the same talk that I gave yesterday. So at the Supercomputing conference, it's all week in Denver. I left the conference yesterday to come here. There were 13,000 people attending that conference. It was kind of scary. So I had no idea. The machine learning conferences, I think, are not quite as large. Maybe they're limited in number, I'm not sure. So supercomputing is actually bigger than machine learning. Who would have thought? Right? I was blown away. So, and the audience yesterday, there were 4,000 seats. Not everybody goes to all the talks. Some people go to the vendors and everything. I don't think I ever spoke to 4,000 people in my life. So you know, I like this much smaller group. It's much more intimate, much better. But I wanted you to get the scene that I'm talking to people who do supercomputing. And these are folks, supercomputing in my mind, I don't know if this is sort of a bad stereotype or not, but it's sort of I think of it as a very conservative field where things just don't change. You know, I kind of remember when I visited, sometime around 10 or 15 years ago, the fastest supercomputer in the world was in Japan. Now it's usually a race between the US and China, but back then it was in Japan. And I got this wonderful tour of this computer. It was called the Earth Simulator because they were doing weather calculations and earthquake calculations and climate calculations. So it was called the Earth Simulator. And this fellow took me around, showed me this big, huge facility where the supercomputer was housed. And I asked him, so what language do you program this machine in? I was curious, what language do you program this in? So my host was really funny. He had a lot of jokes along the way. And to this question, he kind of got quiet. And then he let out a little smile. And these are his exact words. I couldn't make this up. He said that I don't know what happens in the United States, but in Japan, we respect our elders. We all program in Fortran. All right, so here I am at Supercomputing, and I want to promote a new way of programming high-performance computers. And my point was that I feel that we've, in some sense, missed out on the big, real intellectual problem of high-performance computing. It's not that I don't like algorithms. Algorithms are great, but that wasn't the big problem. It's not that I don't like applied math. That's kind of my favorite subject. But that's not the big problem of high-performance computing. I claim that the biggest issue, if we want to get the impact from 13,000 to 13 million to 9 billion, which is the population of the Earth, I claim that the big problem is actually language, the actual business of what programming language to use. How are we going to get there? This is the issue of high-performance computing. And so I was trying to push the issue of language to get performance, right? So we often think of lots and lots of ways to get performance, but I claim that the biggest issue that stands in the way of performance, see, I'm up there on the soapbox, so I get to say whatever I want, right? So I'm saying it's performance is the issue, and also for productivity. So the way we program parallel computers these days is terribly unproductive. It's kind of sad of how unproductive it is. The power of language for impact, and so impact is an interesting thing. Performance is subsumed under impact, but in the world of supercomputing, performance has become the critical issue only. It doesn't matter if anyone ever uses your code, right? I mean, what's wrong with the story, right? You measure performance, you put it in your paper, and if your performance is great, you get to feel like you've been a good boy or girl. Like, what's wrong with the story, right? If you're going to write software, you should have lots and lots of people use it, right? You should do something with it, right? Or, figure out something completely performance alone should not be the be-all and end-all. It's important, it's valuable, but it's not the only thing, right? And so, impact, how many users or what you do with this. Maybe I'll share, there's something sort of was obvious. I've been working with climate modeling people. And, we're all afraid about what's happening to the Earth. The temperature is going to rise by, between 2 to 5 degrees centigrade, in the next decades or so. Nobody knows for sure exactly how much. And then I heard a talk, which, of course, it's not, the fact that the Earth is warming is not the big problem. The big problem is it's how it's going to affect human beings and the things we care about. We care about, some of us care about, our livelihood. Some people care about animals. Some people care about different things. The fact that the temperature is rising is not the problem. The problem is how it's going to affect us. That's the problem, right? Performance is not the issue, right? What we do with performance, that's the issue. Okay, but the power of language for abstraction, which lets us do things. The power of language for community building, which is kind of a favorite topic of mine. So ever since Julia came out, all of a sudden I'm working with all kinds of people around MIT and around the world, people I never would have worked with before. I've made a lot of friends, people in the business school, people, like I said, the climate modeling people, people in the various branches of science. Very often there's a lot of talk about interdisciplinary teams. Right? But, how does it work? You get people from different fields and you throw them in a room and you pretend we're going to talk to each other. It doesn't really work. But language lets you do that sort of thing, and that's kind of fun. I'm a big fan of code reuse. So when I spoke to the students, I mentioned that if you copy code from somewhere, maybe your own code or other people's code, and you change things a little bit, there's something very unproductive about that, right? Why are you copying and pasting code? The code should exist, and you should be able to somehow run on top of it. Language to engage students, of course, that's what we like to do when we're professors. Since I was at an HPC conference, I thought I would kind of finish my title side sequence with the power of language for HPC. So again, you're seeing kind of an encore performance. So I thought I would start my talk with a little social studies exercise that my kids did when they were in second grade. Right now, one of them's in college and one's graduating from high school now. But I think this thing is sort of the kind of social studies project that would have gone on for a long, long time. So comparing past and present, right? So what clothing they wore in the past, in the present. You've seen this game, right? This, thinking about games in the old days, games now, and the Supercomputing conference, it goes on each and every year, and it is always the week before Thanksgiving, right? So this is the week before Thanksgiving. It's been the week before Thanksgiving since 1988, and so I thought I would make a little comparison of Thanksgiving, past and present, the week before Thanksgiving, to talk about the supercomputing conferences. So I'm not even sure, but I think my first supercomputing conference was 90. The first one ever was 88. Maybe I went to that one. I really don't remember, but I thought I would just pick the one in 90. It was in New York. I probably went to that one. Let's just say 90. And the one this week is over in Denver. Okay, so there's 30 years of supercomputing conferences every year. Okay, back in 90, I used this machine called the connection machine. Anybody under the age of 30 never heard of this machine, but it still wins the beauty contest of the best looking computer that's ever been built, right? I promise you, the CM2, this big cube, very well designed. So the company that built this machine was called Thinking Machines. I don't know, does anybody here remember that company? Okay, yeah, over the age of 30, I'll just say that. It was a great machine. When I was a graduate student working with Nick Trefethen, it was actually Nick's idea that I should go wander over to this company and learn something about parallel computers, while writing my thesis. So I did, and then I learned something about parallel computers while I was writing my thesis. So that was back then. There's a picture that, one of these obligatory pictures of me over a summit, which is the fastest supercomputer in the world right now. Actually, they just came out. I didn't check. They must have come out either yesterday or today. It comes out every 6 months, usually simultaneous with supercomputing. So I don't know if this is the fastest anymore. Maybe someone can look that up. But anyway, this was the fastest. Summit's the fastest computer in Oak Ridge, based on the LinPack benchmark anyway, which is a solution of a big linear system of equations, dense system. Their summit is another. Sorry, there's, which is, sorry, Sierra is the other one. But anyway, so I wanted to sort of make a sort of then and now kind of picture of supercomputing. So back then, performance was the only thing that mattered. I knew I was kind of, when I said this, I knew that like people might throw tomatoes, but people were polite. But I said that now the key metric needs to be impact, right? As I said before, performance should be subsumed under impact. Obviously, the better you perform, the more impact you should have, right? But I wanted to emphasize, as I said before, that performance shouldn't be the only thing. This is again a bit of a philosophy of mine, and when I met with the students, I sort of was able to talk about this. But in the past, users ran something, they got a performance number, they got a result, they reported it in a paper. Okay? That doesn't fly anymore. Now we have to have reproducible science, right? It has to be the case that if you write software and you talk about it in a paper, other people should be able to run your software and see whether they get the same results and see what you've done. In fact, with these climate models, I go to these talks and people report sometimes it's climate science, sometimes it's economics, and I realize that people say what they've done, and I don't know, I mean, I get the big picture, but I really don't know what they've done. And until you look at code, it's actually, you never know what people are doing, right? Talks just don't do it. I mean, you need the spec of a software to really know what's going on. So if your software is not, if you can't look at it, if you can't look, I'm completely against closed source software right now. If you can't see what's underneath the software you're using, you don't know what you're doing, right? So that's just reproducible science. It's the only thing that works in this century. Okay. Composability. So I'd like to talk about. For years I've been teaching the graduate course at MIT on parallel computing. And I have a favorite old homework assignment that I used it once and never again. It was too mean. I didn't realize how mean it was. It wasn't meant to be mean. So here's part one of my homework assignment. Go on the internet and grab some code written in MPI, which is sort of the way a lot of parallel programs are written, and make it run. Okay? It could have been any program at all. I didn't make a thing about it. Just make it run. These are hardworking MIT graduate students. They work almost as hard as you guys, but they work really hard. And most of them got something to run. Okay, then part B, take two programs and make them run together. I mean, it could be like as simple as invert your matrix and now take the FFT of each column. I mean, I told them it could be anything they want. Just make your programs compose. Nobody could do it. Okay, this is a problem, right? In our minds, math composes all the time. You don't think about it, okay? But this is the real world here. This is software. Okay, this is a problem. This is something we need because nowadays it's even worse now because people want to run on ordinary CPUs. They want to run on GPUs. NVIDIA's pretty hot, but AMD and Intel are coming along. Google's has its TPUs. So many different kinds of hardware, and we need these things to be able to continue to run. So composability, everyone needs. Portability was discussed, but kind of lip service in those days. Right now, this sort of heterogeneous computing, all these different processors, it's now a must. Okay, back in those days, the way people programmed parallel computers was a kind of sort of message passing system that came out in the Jackson Garris group at Oak Ridge called PVM. Do I even remember what it stands for? Parallel Virtual Machine or something? I don't remember what it stands for. Then a couple years later, MPI came. How many of you actually programmed in MPI or done something? Oh, quite a lot of you. That's great. So that's the message passing interface. That's starting to show some signs of age. So it's still the way people do it, but it's definitely, there's got to be something better. There's got to be. I mean, come on, there's got to be. All right? So when I started, it was a very small, young community. Nowadays, you guys have lots of things you could do. There's so many competing choices for the sorts of things you can work on. Back in those days, there were some industrial connections. I think that supercomputing, though, I mean, yesterday on the floor, I saw so many. I mean, it was amazing what the industrial connections were, but I think we could have so much more. I think that somehow high-performance computing remains in a little bit of a silo, and it's not fully connected. The big data people are, of course, doing their own version of high-performance computing. It's still in its own little world to some extent. I don't know. I feel like we could do better. So as far as the workflow for success, well, the stereotype was always roll up your sleeves and performance engineer. The more you do that, the better off you are. Now we have sort of a lot more higher level workflows. And here's this evolution that starts, libraries of software is one way you can give a lot more people performance. You can sort of expand on that with SDKs, or DSLs, domain-specific languages, or the hardest thing of all, but the most valuable thing from my point of view, is high-level language, and that is the subject of today's talk. So really, as much as I would love to talk to you about math or other things, today's talk is only about one thing and one thing alone. It's about high-level language. It's about language for parallel computing, and why this is the key important intellectual subject, right? So that's, and there's kind of a precedent for this. So I put up some philosophers and mathematicians, and also one of my graduate students. So he was so proud to be in this club. It was kind of nice. So the idea that language matters is not a new idea. It's kind of obvious, but a lot of times we don't think about it when it comes to computing. We actually, there is a kind of philosophy that says, I don't know, something like this. All computing languages are the same, and by the way, leave me alone, I only know this one language. Right? That's kind of like how most of us operate. Right? They're all the same, but leave me alone, there's just this one that I'm going to use. Right? But historically, people, philosophers, mathematicians, had noticed that language serves an incredibly important role. It tends to define, it actually, Bertrand Russell said it positively, Wittgenstein said it sort of more negatively, but it basically defines what it is that you can express. And if you could say what you can express, it's going to influence your world, right? Wittgenstein said that if you limit your language, you'll limit your world. Russell said that it basically, gives you the medium, essentially, to express whatever thoughts you want. I saw this quote by the mathematician Poincaré in a museum in Paris a while ago. The quote was really, really long, almost too much language, so I kind of shortened it. Where he basically was talking about how ultimately if you choose the right language, the right notation, mathematics is amazing, right? If you make it all very clunky, then the mathematics is just that, it's clunky. So that's my paraphrasing of what Poincaré was trying to say. But that, if language and notation is very well chosen, it's just astonishing what you could do. And then there's Valentin, who found me all these quotes. Poincaré I saw in the museum, but he found me the Russell and Wittgenstein quotes, who basically says that computer science language is really applied psychology. And if you have the right kind of language, we can coax people to write better programs. It's like notation. But it's even better because you can get performance. You can get people to work together with the right language. So, all right. So there, I hope I've established that there's a precedence that programming language is somehow the key intellectual question that mattered. So, this is also not a new question in the high-performance computing world. So starting a little over 15 years ago, I guess it was it started about 17 years ago, the DARPA, the defense agency, put some money into languages that would both be highly productive and high performance, right? And so high productive and high performance was sort of the idea. And 3 languages came out, Chapel, Fortress, and X10. Fortress and X10 are completely dead. Nobody uses them. Chapel is still being pushed by Cray, but I'll bet anyone here use Chapel? Anyone? I didn't think so. Okay, I kind of figured nobody's using Chapel. But Cray it's still alive, and Cray is still pushing this. So, of course, I'm going to move up to Julia in just a moment. But I want to focus on productivity and performance because there's another notion out there that people believed, and when we created Julia, we wanted to basically shatter a belief. There's often this belief that a programming language can either be easy to use, like on the human, like a high-level language, but you're going to pay a price with performance, right? Like if everybody knows that Python is like slower than C or something, right? So if it's easy to use, then you're going to pay the. I mean, of course, you could call library software, and in that limited case, you could get the same performance as C. But basically, people believe that if something's high level, you're going to pay the price with performance, or on the other hand, if you've got a highly performing language, then you're going to have to work very hard and use a lower level language that can be a little bit harder to learn. I mean, it does, lots of people use these lower level languages, and maybe many of you do, but there's always been this thought that it's some kind of trade-off. So we invented Julia in part to show people that this is not a trade-off at all. It's just a happenstance, right? And so, okay, but in any event, since I was talking to a supercomputing crowd, I thought I would kind of bring this back into the supercomputing kind of story. And so this is at the big Denver Convention Center. It's still going on. If you want to take a flight to Denver tonight, you can go to the Denver Convention Center downtown. I'm sure these panels are still up. And on these panels, it was a very nice historical sequence going back to 1988 of all the supercomputing conferences, one every year. And I looked at these panels one by one. And I started in 1988, and I noticed that on the bottom of at the lowest line on these panels, you can't read them from my picture, but on the lowest line, it mentioned programming languages, right? And in 1989, it said programming languages. In 1990, and so forth. Every year from 88 to 2010, for whatever reason, 2005, they missed it. But otherwise, from every year from 88 to 2010, a programming language was mentioned. Right? Sometimes it was high performance Fortran. Sometimes it was, once it was mentioned, it was MATLAB. The different languages were mentioned every year. And then there's the current decade, right? So we're about to end the second decade of this century, right? We've got only a few more weeks to the second decade of this century, right? It ends with 2019's end. And if you look at all the years from 2011, that's this, I guess this is this red one, if I can. Right, so 2011 sort of, is that red or yellow? I can't even see. But this one, and then all the way up to 2019, which is at the end, no mention of programming languages at all. So I call it the dark decade, right, the dark ages. Right, something seems to have gone wrong. Right, so I actually I asked in the audience, I don't know who makes these panels, but if you're here in the audience, can we get them back in 2020? So what went wrong? So there's this notion that you build a parallel language and people will come. And of course, some people do. I mean, right now, there are people who are learning to use CUDA to get to I mean, how many of you program in CUDA? See, look at this. People will code CUDA to get performance, all right? But you're not going to get millions of people, right? You're going to get some of you. You folks are motivated. You're learning CUDA. That's terrific, okay? But you're not going to get the large impact out of a language like CUDA. But people will come. Some people will come. People used Fortress and Chapel and X10 back in the day, right? So some people will come. But if you want to talk about big impact, what we decided was that you really need a multidisciplinary user base to start with. You need a really good serial language that performs. And so there were a number of things that you need. I mean, I'll just mention a few sort of computer science-y terms. But basically, we decided you needed the user base. And so we built a user base for Julia. And so people have been asking me, like, where are people using Julia? Julia's all over the place these days. I mean, here are some universities that are teaching Julia. But in fact, what you can do is here, I'm going to just go to julialang.org. And if I'm still on the internet, you can go to this webpage, and there's books about Julia these days. Here's a ton of books that are being written. I mean, this is what a user base looks like, okay? Classes being taught all over. Any Julia classes here at the university? Maybe it's time. You guys could be the first. So University of California, if I search for Washington, will any Washington come up? No. Yeah, see, we've got to fix that. All right, you guys can fix that. But in any way, it's being taught in lots of places around the world. Okay, so these are my three co-founders of the Julia language. There's Stefan Karpinski, Vril Shah, Jeff Bezanson. Jeff is sort of particularly notable because he named Julia. It's not anybody's mother or girlfriend or the mathematician. It's just a good name for language. People always ask. But Jeff was determined to create a language and call it Julia. And in fact, there were 3 Julias before the current Julia. So he was absolutely determined all his life to create a Julia, whatever it would be. So the other thing we knew is that to create, we had some notion of the lifetime of a language. We knew that it would take 10 years or so before anybody would take us seriously. I mean, you start working on a computer language, and I promise you that nobody cares, right? It's like, oh, that's nice. Now, get back to work, right? It takes about 10 years before a language starts to catch on. And we are right now in that 10th year. So this is like the cusp of things catching on. And we knew it. When people would say, like, why bother? What about Python? And they'd be like, fine, whatever. We didn't really talk. Well, the one thing that the old adage that if you want to do something like this, you just have to sort of, start and do what you think is right and, let the time go. And so patience is for sure a virtue for this sort of thing. All right. Since a lot of the folks in the audience were at the national labs, they do some of the biggest computing, I started to put together a little bit of a collage of Julia at the national labs. This is far from complete, but these are a bunch of people. There's Jane over there who actually basically organized our last JuliaCon, did her PhD at Caltech in physics. There are people, lots of friends here and all around. Here are some numbers. When you have an open source language, it's kind of hard to really measure how many real users there are. So these are sort of proxies, not necessarily like a count of how many real users there are. But these are some numbers that we can measure. Sometimes like Stack Overflow is like the best measure, just to watch the trends to see how quickly a language is growing. But anyway, here's some numbers because people always ask. So I put these numbers in. But what I want to do is give you a live demo of sort of the dream for Julia for high performance computing. And so this is what I do. I like to do real live demos because as I said, the software is as important as the paper, right? That's what I truly believe. And so I'm going to sort of put my money where my mouth is and give you by the way, I did this in front of the 4,000 people, which is really scary because software is very, you never know it'll work. I had a backup PDF just in case, but I was going to do it, and I did it. It worked out okay. So, and I'll, maybe cross our fingers it'll work out okay again. So I'm going to run a little Julia here, and I'm going to try to give you kind of the feel of. It's kind of hard to really tell you what I really love about Julia. I kind of tell people you have to experience it for yourself. But let me try to give you a little bit of a feel. So I'm going to set up I'm going to run this on a computer in Boston because I have some GPUs over there. So I'm glad the internet's working. But to give you a feel, let me talk about my favorite topic, linear algebra. If linear algebra is your favorite topic, then just listen along. If it's not, substitute whatever your favorite topic is. I think it'll work anyway. So I want to imagine that you're doing a linear algebra problem of some kind, right? Now, if there are lots of really great linear algebra libraries out there. There's LAPACK, which is what everybody uses when you run a dense linear algebra problem. So I don't care whether you're using Julia or MATLAB or R or Python. If you're doing dense linear algebra, I'm pretty sure you're using LAPACK these days. Okay. There's the ScalaPack, which is the scalable LAPACK, which I don't think has caught on so well. But there has been this project for parallel linear algebra. There's also the Elemental, which is done a little better, but still the whole parallel computing thing is not working out so well for linear algebra in ways because of the software issues. There's ARPack, which is for sparse matrices, right? Iterative, or nullity solvers for sparse matrices. So here are some of the libraries that you might call if you're going to run dense or sparse linear algebra. By the way, I'll share what is my biggest and really only contribution to LAPACK. Is I designed the cover. There's a puzzle. There's a math puzzle in that cover. You might have to see the back of the guide to fully appreciate the puzzle that's under it. But that's my only contribution to LAPACK, really. So embarrassed to say. But all right. So back to the main story. All right, you're doing a linear algebra problem. If you're doing a standard dense linear algebra problem, you call these libraries, you're fine, you're happy. All right, you're doing a standard sparse thing, you roll your own, you call library, you're fine, you're happy. But what if you're starting to innovate and do something? Again, this doesn't have to be linear algebra, like substitute your own favorite topic. But what if you're a researcher and you're innovating and you're doing something that's not in the libraries, right? Suppose you want to actually do what researchers are supposed to do, which is advance the world, right? You're doing something that's not in the libraries. I'm going to give you a kind of made-up example, and I'm going to take a matrix where I'm going to make a special matrix. It's my special matrix. And it's where I know something that the libraries don't know because it's my matrix, right? I know my matrix better than the libraries, right? And so this, you see, when you do a demo in an audience like this, if you do something really simple like matrix multiply, like you all can multiply matrices. It wouldn't impress you. And if I do something really, really hard, I wouldn't be able to make my point. So I'm hoping I'm in that sweet spot with this example. So in my example here, I'm going to create a custom matrix. I'll show a picture when n equals 3, but it could be any size. So for my custom matrix, there's nothing special. It's just a demo thing. I'm going to start with a vector of length n. I'm going to call it v. And my matrix is going to be the sum of the diagonal of v, here it is when n equals 3, and the outer product of v times v transpose. So this is sort of the multiplication table of every element of v with every other element of v. Okay, so there's my special matrix. It's the diagonal of v plus v transpose. Okay, nothing special about it, but I like it. It's my matrix. It's my special matrix. Okay, so this matrix, whatever the n is, nobody would call it sparse because it doesn't have any necessary zeros, right? I mean, it might accidentally have zeros, but basically it doesn't have any structural zeros, right? So it's not sparse. But on the other hand, the word dense doesn't feel right either because, of course, you're going to represent this with n storage and not n squared storage. So you're not going to store it as like n squared numbers, right? That would be crazy if the matrix has any size at all. So this is a structured matrix. It's not sparse. The word dense is somehow missing the point. It's a structured matrix, right? This is a matrix with structure. And if you've learned anything about numerical computing, it's all about taking advantage of the structures you have, right? So this is my example matrix. And now let's go ahead, and I'm calling it an SC19 matrix in honor of supercomputing. Let's, you know what? I want to make sure, I want to restart and clear all the output because otherwise you're going to think I'm making it all up. So let's just start all over. Yeah, I don't want you to think I made anything up. Okay, so this Julia syntax is probably the most complicated looking syntax of this entire demo. But all it's basically saying is that my supercomputing 19 matrix is made up of a vector, which I'll call v. All of this punctuation that might look a little scary is all there to just basically say something like, I want to allow my matrix to have floats or ints or quaternions or matrices of matrices, or all the sorts of things we like to do in mathematics, which is basically allow the contents of our structure to be from any sort of mathematical object that you could possibly imagine wanting. Okay, so that's what this thing here is doing. It's just saying that my SC19 matrix is made up of V's. Okay, and then it's the next two lines. Oh, didn't I not clear this? Wait, kernel start. Wait, my kernel's not starting. I shouldn't have done that. Did it start? Come on. Did my kernel start? Oh, am I good? Oh, I'm good. Oh, okay. Everything's good. All right. It's very scary when you do live demos. I promise you, it's really scary. You're always sure it's going to break. So the next two lines actually do define the size of a matrix, which is how many rows am I going to have? Well, it's the length of my vector. How many columns am I going to have? The length of my vector. Okay? So this is the V field of the matrix A. Okay? And if I want the ijth element, this is how I really define what my matrix is. On the diagonal, I'm going to take the ith element, just like the picture shows. And then otherwise, I take the ith element times the jth element. Okay? So now I've used Julia to define my special matrix. Okay? But I'm still using the Julia language. I'm using size. This actually matters. I didn't call it my size or your size or SC's. It's just size. So now, when I apply size to one of my matrices or any of the other built-in matrices, I still get the right answer, which means I can write code with the word size, and I get to abstract away whether it's mine or yours or somebody else's, right? This is where abstraction comes in, right? Or get indexes as well. It's the standard get index. So here, let me just sort of build a 3x3 version. Here it is with the numbers 1, 10, and 100. You could, if you're quick at checking your linear algebra, you can see the numbers are coming out right. In Julia, you can see how something is built. So the dump command, let's just show you the dump of the matrix as well. The dump command tells me that I'm only storing the 3 numbers. I could actually cast it to be an ordinary matrix, and then the dump command shows me that I'm storing 9 numbers, right? So you really want to store n numbers for something that's structurally n numbers, right? Storing n squared numbers would be ridiculous. Okay, so This is my favorite matrix. I love eigenvalues. I love singular values, right? You've known me a long time. I mean, these are the loves of my life, eigenvalues and singular values. So I have a little code here, which Anne here is already understanding why it works, but that's not important. This will get me the largest eigenvalue of this matrix. Okay, doesn't matter how. You don't have to read this. Maybe I should hide it. The main point is I'm using the eigmax command, which is Julia's command in general for getting the largest eigenvalue of a matrix. So that if I type eigmax of one of my matrices, it'll use this one. If I use it on a regular matrix, it'll call it APAC. Or if it's a sparse matrix, it'll call it ARPAC or something like that. So it'll pick the right library or my own software for when it needs it. Okay. So again, if you don't like linear algebra, if eigenvalues are not the love of your life, take your favorite problem, imagine your own custom thing, and the story still remains the same. So here I'm going to calculate eigmax of A, and it happens to be 10,200, I guess. Here I'll cast it into a matrix, so it'll call it APAC, and oh, look, it's got the same answer. Yay, that means my code works. Okay, so this is calling my solver, this is calling LAPAC, good, okay. So now I want to talk about going heterogeneous, so using different kinds of processors. So in Julia, let me sort of run these different things here. So in Julia, if you want to put a vector and have it run basically on a GPU, you can create a coup array. And there's this sort of a little annoying warning, but it's actually a good warning. It basically says that scalar operations are slow on GPUs, which if you've ever used GPUs, you know. I could make that go away, but it's still a good warning. All right, so this is a GPU. This is a distributed matrix. So actually running on a multiprocessor machine. So, I mean, 3 is kind of small, but it illustrates the point that you can distribute the matrix. And there we have now a distributed matrix. Okay, and then of course, just to check, I can cast it back into an ordinary matrix, both the GPU matrix and the distributed matrix, and it works. All right, but now let's get to the point, the thing that everybody's going to care about, timings. All right, so let me get some of this running, and I'll tell you what's going on. So, all right, so let's do a serious problem. Let's make n be 4 million. So if you know anything about computers, there's no way I'm going to store a 4 million by 4 million matrix on anything other than some of the most expensive supercomputers in the world, right? I don't have access to those machines, though they were on the floor, not far from me when I was giving this talk. But most people don't have access to those. So a 4 million by 4 million matrix stored as a dense array is just not going to happen, all right? But that's not what I'm doing, right? Here I'm going to create 4 million random numbers just for fun. Every time I do it, I get a different answer. But here's 4 million random numbers. Here's the first, the second, the third, ... and here's the 4 millionth at the bottom. All right, so 4 million random numbers. And I'm going to create one of my matrices. It's a 4 million by 4 million matrix. There it is. And of course, I have the illusion of a 4 million by 4 million matrix. I have the abstraction. In my mind, it's a 4 million by 4 million matrix, right? But the data structure is a 4 million vector, just 4 million to the first, right? So I have the illusion of a 4 million matrix, okay? And I'm going to distribute it, and I'm also going to send it to the GPU. And now I'm going to run it directly on the machine and on the distributed computer and on the GPU. So this is not a terribly fancy computer, but when I run it on one processor, it took about 450 milliseconds. All right? I ran it, I'm using 4 processors. Nobody ever gets a speed up of 4 on 4 processors. What did I get? Maybe barely a speed up of 2. Well, that's respectable enough. Distributed computing, all right, I got 200 milliseconds, which is like a divide by 2 almost. Okay, and then ran it on the GPU. Did I run it twice? Did I get to this one twice? Oh, yeah, just to get sort of the fair timing. Okay, yeah, so on the GPU, I got a better result before, but I have a feeling somebody else is using the machine, but that's okay. Right now I'm getting 117 milliseconds using the GPU, which is respectable, but I have a feeling I should be able to get better. But in any event, that's not the important part. The important part is how easy it is for me to parallelize, use GPUs, right here, right. This is how parallel computing is supposed to be, right? This is the dream. We do some of this right now. Some of this is a research problem, but there's the dream. So let's talk about what the real dream here. It's the very dream of mathematics. It's the dream of abstraction, right? That's what the whole thing about language is about. I just kind of threw two abstractions at you. Maybe you saw this happen, maybe you didn't. But let me be very clear about the two abstractions, right? There's the one abstraction that I mentioned, that this 4 million by 4 million matrix, this thing that's in your brain, right? In your mind, it was a 4 million by 4 million matrix, right? That's the abstraction. In the real world, it was just a 4 million vector, right? It's not an n by n in storage, it's just an n vector, right? And all my algorithms run, if I give it the specialized algorithms, they'll run on the n vector, okay? And so if I'm smart enough to figure out how to do everything on that n vector, I can get better algorithms for everything with my matrix. So the first abstraction for the matrix takes the real live n vector and treats it like a matrix. The second abstraction is doing sort of the same thing. It's treating a matrix that's distributed on GPUs or on parallel computers as a 4 million by 4 million matrix. In other words, whether it's something mathematically structural or if it's something about how I'm storing my matrix, it's still, to me, the abstraction of a matrix. So when I go ahead and write my algorithms, I am writing algorithms on matrices, right? I specialize when I need to, but otherwise, I'm thinking of this as a matrix. Abstractions is where you get power. Everybody, this is like the first thing you learn in computer science, that the abstractions are where power comes from, right? And so what we need in numerical computing, what we need for parallel computing is getting these right abstractions up and ready, okay? It's not about taking math and turning it live. It's about actually getting the right abstractions for all of us to be empowered, right? So why Julia? Well, this is sort of a long, complicated story, and it's very hard to explain it in a short talk. But I've just listed a few of the pieces that make Julia work particularly well to do just this sort of thing. So we have the well-designed abstractions. We have something called multiple dispatch, which basically says that if you look at the arguments to any function, you can decide what program to run based on the types of everything, right? So if you have a real matrix and a complex number and an integer, you can actually pick based on that. That's multiple dispatch. We have this very careful balance between the static and dynamic. So static means like it's compiled. Dynamic means it's something like, on the fly you do things. So we've got a balance. There's lots of different things I could tell you. LLVM is sort of a big deal. I don't know if you don't know what LLVM is. Let me just quickly say that compiler technology has changed a lot, and there's this wonderful program. I guess it was originally out of Illinois, if I remember correctly. Basically, lots of software is compiling down to LLVM. It basically means that you can compile down to LLVM, and then various optimizations could happen at the LLVM level. So many things are doing that these days. So Julia does that, and that's kind of a little bit of our secret weapon. But just compiling to LLVM alone is not enough. You need this type inference that's going on. And by the way, Julia plays nicely with Python and also legacy parallel codes like MPI. People have hooked up MPI codes to Julia, and it's kind of given them new life because other people could run it. So why Julia is a long story. We like to refer people to this paper if you want to know more. So you're welcome to do that. All right, but I'm going to go back to my slides to finish up my talk. But at the risk of repeating myself, the real secret is abstractions, getting the right abstractions. That's what it's all about. Okay, so back to the slides. So I had a couple more slides on who's using Julia. Maybe I'll just share them quickly. But there was this machine learning application that was involving mapping the heavens. I don't know if you can even see this with the light washing it out, but this was an application to catalog the visible universe. It came out of Berkeley Labs. We worked with these folks a little bit. And what made this important for us is it got us into the petaflop club. So the people are talking about exaflops. Again, I don't know what your background is, but a flop is a floating point operation, like a plus and a times. If you ask yourself, if you can multiply 3 times 5 in 1 second, without a computer, you've just executed one flop. Okay? A megaflop is 1,000,000 of those things, 1,000,000 operations in a second. What does it come to? A gigaflop is another factor of 1,000. Then a teraflop is another factor of 1,000. And most computers, like laptops, tend to work in the gigaflop range. Supercomputers have been running in the petaflop range, which is another factor of 1,000. And then the biggest computers nowadays are in the exaflop range, which is yet another factor of 1,000. Right? So this brought Julia into the petaflop realm, and it's the only high-level language to ever make it into the petaflop club. So that's sort of the significance of this. There were some Intel people in the audience, so I sort of shared this slide. But let me sort of move on a little bit in the interest of time. So I mentioned that I've made friends at MIT and around the world in different areas because of language. So I'd like to share this story about climate models. So I don't know anything about climate models, really. I mean, didn't, you know. But but there's this big climate model. Climate science is really important right now. And there's this big climate model that's kind of being run out of Caltech with Tapio Schneider. And there are three folks at MIT, Chris Hill, Raf Ferrari, and John Marshall. Are the MIT people who are involved with this. And the MIT crowd, they came to my office and sat on my couch, and they said to me, Alan, we are throwing away our legacy Fortran code. Don't talk us out of it. Right? We're not going to use it anymore. Nobody understands it. Nobody knows how to maintain it. There's so many better algorithms these days. It took us a long time, but we're finally going to throw it all away. I'd never heard that before. It's usually, we can't live without our legacy code. This is what you usually hear. But we can't stand it anymore. We're throwing it away. We want to use Julia. Don't talk us out of it. That's another thing they said. But we're not sure. We think we want to use Julia. What they said was, well, we have this handwritten CUDA code. And we know that Julia's abstractions are really nice. We know that this is this really beautiful language to execute. But we are worried about performance. So here's a little challenge for you if you want to accept it. We're going to give you 4 weeks. And if you can reproduce from Julia the same, well, I'll tell you what. We'll give you can go a factor of 3 slower. We'll take that factor of 3 for the beautiful code. All right, we're going to give you a factor of 3 slower. But you have to, in 4 weeks, we want to see you get within a factor of 3 of our handwritten CUDA code. Oh, that sounds like fun. So we did that. And the students, they worked on it. Didn't take them very long. We got the factor of 3 times faster than the CUDA code. Why were we able to do that? Right? How could you beat people handwriting CUDA? How's that possible? Well, the answer to that has to do, and I'll kind of sort of tell a little bit of the story, which is the power of high-level language. You don't realize this, but the code that we wrote looks a lot like the math, right? So this is a shallow water reservoir model, and the 2 boxes over there are the LaTeX, and the 2 lines above it are, at the highest level, the Julia code that actually executes the same thing. I mean, it looks kind of like the math. So you can use Unicode. You can have math symbols. You can have aliens and cats. And cats can be variables, like pictures. You can do that. I'll show you if you don't believe me, but you could. Here, let's do it. Why not? In other words, you're not going to believe me. So here, let's. Assuming this is still. Let's see. Can I really do aliens? Let's see. So if I go, can I type aliens or not? Yeah, there's an alien. So okay, so there's my alien. I can go alien equals 42, right? And I can go alien squared, right? The real thing is that it looks like the math, right? So here's an alpha, and once you start using Greek letters like this, the idea of typing this looks so disgusting, you'll wonder how you can ever type those 5 letters again, right? I mean, you want your code to look like the math, right? This is not math, right? This is alpha. This is math, a Greek letter, right? This is actually executable code. There's stuff underneath that does all the hard work, of course. But the point is, if your highest level code is written in a high level language, then you can make changes to your code. Small changes will have a big impact. If you go down to the lowest level quickly to get performance, you write that CUDA code because your advisor said that's how you're going to get performance, right? You'll write that code and you'll probably get the performance, and you will never change the code again because you will never look at it again, right? Because it's too hard to. And by the way, if you let go of that code, you leave that group. Nobody else in your group will ever change that code again. Maybe you'll remember what you did for about 3 weeks, but nobody else will ever know what you did, right? And you won't remember it even after. So, but when you have a high-level code, you can make big changes with small bits of, you have a lot of leverage over your code, right? I mean, it's saying the obvious, but that's kind of how we get that power in Julia. All right? I have a couple of more slides. I'll just go through them real fast to finish up on time. But a little bit of how do we do it. This is really a little bit more for the computer scientist. But basically, we don't transform to CUDA. We transform to what's underneath CUDA, which is PTX, right? And so what we do is basically, in this box is sort of the pure Julia part of it all, which, as I said before, compiles down to LLVM. And what we do is we pull off the pieces at the right levels. And so at the very lowest level at LLVM, we can grab code and generate PTX for NVIDIA's GPUs, right? And then we can go ahead and do this for other processors too, like the AMDs or the TPUs that are coming out of Google, the tensor processing units, which we've done a little bit of as well. But we can also grab it at higher levels. We can grab code from the Julia compiler and send it also over to the GPU. And thereby we get code reuse. We don't rewrite everything for the GPU. We take our compiler code and simply omit the code that's needed for the GPU. It's a much easier problem to solve. So that's a little bit of a feel of how we do it. So some people have asked me about what are Julia's active areas. It's such a big answer, I don't really know how to say it, but here are some of the things that I'm rather interested in. And I mentioned this to some of the students, but something that's very exciting is neural ODEs, which is the idea of doing machine learning tool chains where you don't have matrices inside your neural networks with parameters that don't tell you anything about your physics, but you replace it with differential equations with parameters where you can actually tie it to the physics. And Julia seems to be doing particularly well with that. Chris Rakakis, who's in my group, an instructor at MIT, is just leading the way. He's doing fantastic things with that. So I'll just pull that out. With the high performance computing, the message that I'd like to share, and maybe this is sort of the key message, is when you write up math for your computing, don't say what you want. You should say what you want to compute, not how you want to compute it. I promise you that'll be much more long-lasting. Say what it is you want. Don't go into the details of it. Lower levels, you can say how you're going to do it. At the highest level, just say what you want. You'll get a lot more composability. You'll get a lot more performance in the long run. There's a lot I can say, but right now, Julia is a high-level parallel computing language. We can do all kinds of parallel computing. We could do distributed. You can use MPI if you really want to. We don't encourage that. But we think that the big HPC language problem, the one that remains a research problem, is how to express all algorithms in a high-level language. And whenever I bring that up, there's always the knee-jerk question. Maybe some of you are already thinking of it, so I'm going to anticipate it. But how do you distribute this problem on this machine? How do you carve up your problem? The answer to that question is an NP-complete problem. We know that. How do you carve up a problem? We know the inputs, right? We know there's compute, there's communication. That's all there is, right? You've got hardware, and you can compute with it, and you can move your bits around. The problem is simple. The question is how to optimize that, right? What we're looking for is heuristics to be able to do this for all sorts of problems. Okay? If everybody's writing their own one little answer and nobody's working together, we're probably never going to solve this problem. But in an open source language where we open this up and we ask lots of people to help figure this out, we can solve this problem. So we could stop saying this is too hard a problem, nobody knows how to do it, and we could actually start actually solving the problem. And this is what I want to see. And so I gave a list of some of the things that we're trying to do right away to sort of get a handle on this problem. I'll be a little bit honest and say that I put this up in the hopes that some of the people in my supercomputing audience with some special skills might take on my request to help out with some of these things. And so I just sort of threw it up there. But really my message, and this is my last slide, is that we really want people to participate in this great effort to finally solve the expression of the HPC problem. And we are asking people to participate. You can participate on Discourse or Slack. I invited people to talk to me or even to email the Julia Lab. One person in the audience emailed Julia Lab before the slide went off. And Valentin answered him before the slide went off. So that that was at 9:30 Mountain Time, which was 11:30 on the East Coast. We were getting a little late. It's now 8 p.m. on the East Coast. So I don't know if Valentina will answer today, but if you want to try it, go ahead and say you want it, but you got to participate now. You got to be a Julia person now. So anyway, so that's my language story. Thanks for listening.